So today we'll be covering Coulomb's law. Coulomb's law is a very important concept within electrostatics and physics E&M, and we'll be looking at a couple examples, going over definitions, and understanding why Coulomb's law is really, really important and how it governs everyday objects within our daily lives. So let's get started. So what exactly is Coulomb's law? Coulomb's law dictates how we feel forces and the electrostatic force. Suppose that we have a charged object. We have a charged object of value Q1, and then we have another object of Q2. The sort of force, whether that is attractive, repulsive, in any sort of direction, is the electrostatic force. So Coulomb's law is electrostatic force between charged particles. The formula that we're really going to have to understand is F equals K Q1 Q2 over R squared. The terms within this formula are going to be the force, the actual electrostatic force that we're measuring. This is the magnitude of electrostatic force. That force is going to be measured in newtons. We have a constant, the electrostatic constant, Coulomb's constant, is going to be 9 times 10 to the ninth Newton meters squared per Coulomb squared. We have the actual values of our charges. In this case, are going to be the value of Q in Coulombs. And mind you, a lot of times charges are measured in values of microcoulombs because they're very small charged particles. And then finally, we have the value of R, or the distance, the straight line distance between those two charged particles. So R is going to be distance between particles. Now, it's really important to also look at the polarity, whether if it's a positive charge or a negative charge. If we have two positively charged ions, or two positively or two charges of the same polarity, the electrostatic force is going to be repulsive. And on the other side, if we have different polarities, this is going to be an attractive force. So right away, if we have two positively charged ions, we're going to have a repulsive force. And if we have a positive and negative charged ion, we're going to have an attractive force. This is really where the phrase opposites attract comes from, this phrase that is really defined by Coulomb's law. Let's look at a couple of examples and understand how the numbers really work out in this case. So here we have a value Q1, which is positive 3 microcoulombs, and another charge Q2, which is going to be positive 2 microcoulombs. The distance between those two said charges is going to be 0.5 meters. And we need to find the magnitude of electrostatic force and state if it is attractive or repulsive. So right away, we can solve this problem in a couple of quick steps using Coulomb's law. Let's get right into it. Step number 1, let's write Coulomb's law. Write our formula. That is going to be F equals K Q1 Q2 over R squared. So what exactly do we even have, and what is given to us in this question? So we have the value of K, that's going to be 9 times 10 to the 9th. We have value of Q1, which is going to be positive 3 microcoulombs. We have value of Q2, which is going to be positive 2 microcoulombs. And we have that straight line distance R, 0.5 meters. So right away, we have everything that we need to solve this problem. We can simply plug and chug into our equation. So step number 2, plug in. This is going to be F equals 9 times 10 to the 9th multiplied by plus 3 microcoulombs multiplied by plus 2 microcoulombs, whole thing over 0.5 squared. So now that we have our plugging in formula, we can simply plug this into our calculator and get a value of 0.216 newtons. which is the magnitude of force. We still haven't solved this problem fully, though. We need to understand if it's an attractive or a repulsive force. This is pretty easy in this case, though. We have two positively charged ions, two positively charged charges, and therefore we know that this is a repulsive force. So suppose we let these charges eventually go. Where would they really, where would they actually end up? These charges, Q2, would be moving this way, and charge Q1 would likely be moving this way without any sort of other interference. Let's move on to another example. Example number two. Example number two is a little bit more challenging in this case. It's pretty similar to the last example as well, but we've thrown an additional tweak into the question. So in this case, we have two charges. Once again, we have a positive 2 microcoulomb charge and we have a negative 1 microcoulomb charge. We also know that one of the charges is a 0.00 or the origin, and the other charge is at 3, 4, which is diagonally up from the other charge at the origin. We need to find the magnitude of force and explain if it's repulsive or attractive, very similar to the previous problem. So, like the previous problem, we're going to use the same exact steps. So, step number one, write the formula. That formula is going to be F equals K Q1 Q2 over R squared. In this case, we have the value of K, obviously. We have value of Q1, we have value of Q2, but do we have the value of R squared? See, we know where each point actually resides, but we don't know what the straight line distance between both of those points really is. Therefore, we need to actually find what this dotted line distance is. Fortunately, we can use a very simple distance formula to actually calculate that based on the coordinates that we're really given. So, step number two, solve for distance. That distance, let's call it d, equals x squared plus y squared. In this case, we already know what those values of x squared and y squared are. That's going to be 3 squared plus 4 squared, take the full square root of that. That simplifies to d equals 5 or r equals 5. The d and the r in this case are interchangeable for our purposes. Therefore, now that we found r, we can finally use Coulomb's law and plug everything in. So let's divide everything right there. 3, plug into equation. We have F equals 9 times 10 to the ninth. We know that. We have a plus 2 microcoulomb charge. We have a minus 1 microcoulomb charge. And we know that the distance is going to be 5. We'll take square of that. Once we plug that into our equation and that into our formula, or into our calculator rather, we get a value of 7.2 times 10 to the negative fourth newtons of force applied on each of those charges, since we know that force is going to be opposite and equal. Now that we've calculated the magnitude of the force, however, we still are not done. We need to figure out whether it's attractive or repulsive. Fortunately, this is a pretty easy sort of question. We already know that these charges are opposite. One of them is positive, one of them is negative. Therefore, we know that this is going to be an attractive force. The second part of our question. Therefore, if we extrapolate this and change the time scale, if we release these charges from their set fixed points, we know that our Q1 charge is likely going to move this way right towards our minus 1 charge. And we know our Q2 charge is going to move in the opposite direction right towards until they will impact at some point. So we've understood two examples in this case, one straight line example and one diagonal example. And we always need to solve for the distance, especially when we're not given it or when we're given a bunch of points that we need to calculate the distance for. So in conclusion, what does Coulomb's law really say, and how does it really define the fundamentals of electrostatics? For this, we really need to go into some chemistry and understand what is an actual charge. A charge is going to be something similar to an ion. If we have a positive ion, that means that the number of protons are going to be greater than the number of electrons whizzing around outside of the atom of the outside of the nucleus. If we have a negative charge or a negative ion, we know that the number of protons is going to be significantly outnumbered by the number of electrons. So the number of electrons is greater than the number of protons. This also determines whether if it's an attractive or repulsive force. Attractive being different charges and repulsive being same charges. There's a lot of important applications of Coulomb's law as well. We can use several different types of sensors to measure distance, especially if we know that there are two fixed charges of a certain value and we simply need to calculate the distance between those two things. We can calculate the distance in that r squared denominator of Coulomb's law. Another example is touch screens. Whenever we touch any sort of device or any sort of touchscreen, an electrostatic force is measured on a certain point, and then that point is eventually translated into a separate action based on whatever's programmed for that touchscreen. So another key concept here is going to be on energy and fields, and this is where we're going to eventually go. We know that a charge always has an associated electric field. And this is another concept that we're going to discuss in a later video. So if you like these tutorials and if you like these walkthroughs, please visit us at voltagelearning.com. And don't forget to like, comment, and subscribe and share these videos. Until next time, we'll see you guys later.